Hello everyone, and today we continue our course of formal languages, automata and codes, and we have a new lecture, lecture number 11, with automata, and I recall you that you can find my lecture in this lecture in my web page. Also, the new version of this course in Ukraine you can find also in my web page. Will be write it below in YouTube, and we shall start my lecture. So lecture number 11, weighted automata. Let A be an alphabet with each automaton a capital Q, I, T. Our alphabet A capital with a set of edges E is associated a function denoted by mu A capital in the following way. The function from alphabet A capital to the monoid of all relation on the set of positive integer n, defined by the following formula. So P mu A of LQ is equal 1 if this triple belongs to the edge and is equal to 0 otherwise. This function extends into a morphism still denoted by mu A from the free monoid our alphabet A capital into the monoid of any relation of the set Q, where Q is a set of all states of the automaton A capital, where N is a completion of the semi-ring, such semi-ring. Yeah. In particular, we have that the value of mu A on the empty set is identity relation over the set of the states of Q of the state of the automaton A capital, and we have that the value of this function on the word uv and is calculated in the following way. Assume the following assume, yeah, from any word u and v from the free monoid our alphabet A capital. The morphism mu A is called the representation associated with the alphabet A capital. The correspondence between mu A and the morphism phi A defined is given by the following. So PQ belongs phi A of W if and only if this value is not equal to 0. Proposition. Let A capital be an automaton over an alphabet A for all states PQ and the word W. The value P mu A of VQ is the number of the paths from the state P to the state Q with the label W. A path C from I to T is called successful if the state I is the initial and the state T is the terminal. The behavior of the automaton A capital is a formal power series denoted by the following way and defined by the following formula. The set recognized by automaton A is support of the power series. it is just the set of all labels of the successful path. And it's denoted by L of A as in automata theory. Proposition. Let A capital be an automaton over an alphabet A capital for all words from the Формальні A capital. The power series is the number of successful paths labeled by the word W. A more compact writing of Formula 1 consists in the following formula. Formula 2, yeah. Here, the element I capital is considered as a row, a vector, and T from n power q is a column vector, both with coefficient 0 and 1. Example. Let A capital be a automaton given in the following figure. Yeah, we have the 1 is initial and terminal states. Its behavior is the series, the following series. These numbers are defined by the following: phi0 is equal 0, phi1 is equal 1, and phi1 phi(n) plus 1 is equal phi(n) plus phi(n) minus 1 for all positive integer n. For positive integer n, we have that the function mu a of a in power n is equal the following matrix. Proposition. Let A be an automaton over an alphabet A capital for each integer d of the set the word from the Формальні our alphabet A capital. The formal series is equal d is regular. The proof. Let M be the monoid of Q times Q matrices over the semigroups of BD. What is BD? Is a semi-ring which consists of elements 0, 1, so on, D plus 1, yeah. And the semi-ring operation is the following. So I plus the additive is equal to the minimum I plus, so we denote with this O plus G, D plus 1, and the multiplicative operation is same. D plus 1, yeah. Good. For each word from the Формальні A capital, let alpha W be a Q times Q matrix R as a semi-ring BD obtained from the morphism mu A and W by replacing each entry mu A W in the place PQ by the minima of this value. Since such a replacement is a morphism from the semi-ring N into the semi-ring BD, the mapping alpha is a morphism from a free monoid of alphabet A star into monoid M. The set of the word from free monoid our alphabet A capital, so that such formal series is equal D is recognized by the mapping alpha. It is indeed the set of the word W such that I capital alpha of WT computed in this summary BD is equal D. This completes our proof. To each automaton A capital, we associate the automaton which will denote A capital star and call the star of the automaton A capital by canonical construction consisting of two following steps. Let omega does not belong to Q be a new state, and let B an automaton with the state Q with omega and initial states omega and terminal state omega. Be an automaton with the H F, the following H, where E is a set of edges of automaton A capital and I capital with hat is a such triple where there exists an initial state I, such that I Q belongs to E capital, T is hat is such and there exist terminal states T such that Q AT belongs to edge to E, and O with hat is the following edges. There exist initial state I and terminal state T such that AT belongs to the edge E, yeah, the set of edge E. By definition, the automaton A star is a trim part of the automaton B. The following terminology is convenient to automata of the form such that we have initial and terminal states coincide. Can just the initial state, which is also in a unique final state. A pass from pass C from the state P to the state Q with label W is called simple if it is not a null path, that is W belongs to the non-empty word alphabet A capital, and if for any factorization such factorization of the path T into two null paths, we have that R is not equal initial or terminal states 1, yeah. Any path C from the state P to state Q is the null path or simple or decomposed in the unique manner as in the following way, yeah, where each of these n plus 2 paths is simple. Proposition: let X be a subset of free semigroup of alphabet A, and let A capital be an automaton such that the formal series coincides with the characteristic series of the set X here. And then we have that formal series of A star coincide with star with the formal series of X. Proof: since A star is a trim part of the automaton B defined by the formal, it's sufficient to show that the formal series of automaton B coincides with star with the formal series of the automaton A. Let S be the power series defined in the following way: for all words from Fremenoid hour A capital, we have that SV is a number of simple paths from omega to omega labeled by the with the word W. By the preceding remark, we have that the formal series of the automaton B is equal S star. This is a reminder to prove that S coincide with the characteristic or series of the set X capital. Let W be the word from the Fremenoid A capital. If the word is empty, then we have that S1 is equal x is equal, this value is equal x underline 1 is equal to 0, yeah, since a simple path is not a null. If the word is equal a, which is a letter from alphabet A capital, then the value s on this word is equal 1 if and only if this letter A belongs to the set X according to the formula 6. Yeah. Now we assume that the length of the word W is greater or equal to. We put W is equal U, A, U, B with A and B from A capital and the word U from Fremenoid A star. Each simple path C from omega to omega with label W uniquely factorized into the following way. For some states P and Q from Q capital, there exists at least one successful path. That way, yeah, in automata A. This path is unique because the behavior of the automaton A is a characteristic series. If there exists in another simple path C prime from omega to omega with label W in the automaton B, then there exists also another successful path labeled W in the automaton A capital. This is impossible. Thus, there exists at most one simple path C from omega, state omega to state omega labeled by the word W in the automaton B. And such path exists if and only if the word W belongs to the set A X capital. Consequently, we have that S coincide with the set X capital, which is was to be proved. This completely is our proved. And example, put the set X capital consists of A and A square, then the characteristic series of the set X coincide with the power series of automaton A for the automaton given the following figure. It's here initial state 1, terminal state 3, and start automaton. And the automaton A star is the automaton of the following figure up to remaining renaming of omega, yeah. Consequently, for any n greater or equal to 0, we have that the value of the characteristic series X star on n A in power n is equal Fn, where Fn is the symbol from Fibonacci numbers. So next we put X consists of such words. We have the characteristic series is of X is equal to the power series of automaton A capital for the automaton A of the following figure. So we have that initial state is 1 and terminal state is 4, yeah. The corresponding automaton A star is given the following here. So initial and terminal states omega coincide, and this is automaton A capital star. Now we extend the previous definition to more general case where the labels of the age of the automaton may be vacated. let A be an alphabet and let K be a summary. A finite weighted automaton A capital with state Q, initial state I, and terminal state T hours the alphabet A, and with the weighted of the summary ring K is given by a finite state Q with the mapping I from Q to K and T from Q to K, and by the mapping E from such product here. Q A Q to K. If E P A Q is equal, K is not equal null, then we say that triple is edge with label A and weight K. And in this case, we write such a way. So this pass. If C is a pass, then its labeled is label is X, and its weight is a product K1, so on Kn. We write this pass set Y for denote this pass. The behavior of the automaton A capital is a series denoted by modulo of A and defined by the following formula. Since for each word X from free monoid A capital there exist only finitely many paths with label X. The sum is well defined. The behavior is also called the series recognized by the weighted automaton. The series U is called K rational if it is the behavior of the weighted automaton with the weight in the semi-ring K capital. We will particularly interested in the n-rational series. There is an alternative form of the series recognized by the weighted automaton A capital. Define a morphism U from the free monoid A star into multiplicative monoid Q times Q matrices with the coefficient in the semi-ring K by the setting mu of A is a place PQ is equal EPAQ for any letter A from A capital. Then for any words from the free monoid A capital, we have that the value is equal start with U consider as a row vector and T consider as a column vector. The morphism U is called the matrix representation of the automaton A capital. Example, any automaton can be considered as a weighted automaton with the weights in the Boolean rings B capital or in the semi-rings of the natural numbers and capital. In the latter case, the behavior is a number of successful passes. Example, the weighted automaton on the following figure has integer weight and one letter alphabet. For simplicity, the letter is not specific and the weight of an age is not indicated if it is 1. The value of the behavior on the word of the land n is n in power 2. Indeed, denoted by un, vn, wn, the sum of the weight of the path of the land n ending in 3 and starting in 1, 2, 3, yeah, respectively. We have that wn is equal 1 for all n which is greater or equal to 0. And next, the form the automaton shows that vn plus 1 is equal to vn plus wn for n is equal 0 or greater, whence vn is equal n. Finally, n plus 1 is equal to un plus 2 multiply vn plus wn. And therefore we have that un is equal to n square for any n. Let A capital be a vacuum automaton when I capital is a singleton that is equal 1 for some I from state 1 I from Q, and IQ is equal 0 for Q is not equal I. We write I instead from I capital. The same combination holds for the set T. If the T is singleton, then T of T is equal 1 for some T from Q, and T of Q is equal 0 for Q is not equal T small, and we shall write T instead of T capital. The vacuum automaton A of the following form is said to be trim if for each vertex Q there exists a path from I to Q and a path from Q to T. It is said to be normalized if no edges enters I, no edges leaves T, and I is not equal T. Proposition. Any n-rational series with zero constant terms can be recognized by a normalized vacuum automaton. Proof. Let A capital be a vacuum automaton recognizes a series with zero constant term with the edge mapping I, E from this product to the summary K. Let I and T be two states not in Q, and define a weighted automaton B with the state Q prime, initial state I and T, with the Q prime Q prime is equals a union Q with the set I and T, and as mapping F from this product to summary K by the formula. Then the metric representation nu of automaton B capital is related to the metric representation mu of automaton A capital by the following formula, where I and T are reported as the first and the last index respectively. It is easy to check the same form holds for any words from free semigroup our alphabet A capital. I propose you to prove it. Yeah, as exercise 1. It's very simple exercise. And those we have that the value of interest nu of V in the IT coordinates is equal I capital multiply mu of V T capital. And this holds also for the empty work W, because I is not equal to T, and I capital mu of W T is equal null for assumption. This proves that automaton A and automaton B recognize the same series. Now we consider power series, that is a series in one variable. Proposition: for any rational subset K of a free monoid our alphabet A capital, the genetic set fx of z is n rational. Let A capital be a deterministic finite automaton recognized as a set X, and let B capital be the weighted automaton obtained by replacing all labeled in automaton A capital by the symbol Z. Clearly, the automaton B capital recognizes the following series. I propose you to compose this as an exercise 2. That automaton B recognizes the following series. Given a series U of Z with the integer coefficients with 0 constant terms, U of null is equal to null, we recall that U star of Z denotes the series defined by the following formula. And then we have the proposition. Let U of Z be an irrational series with 0 constant terms. Let A capital with a state Q and initial state I and initial state T be normalized with the automaton recognizes the series U of Z. Let our line Q consist of Q without T, and our line A with B will be automaton with the state Q, our line Q and initial states and terminal states I. Be a weighted automaton obtained by marrying I and T. Then the behavior of the automaton A, our line is a series U star of Z, yeah? Proof. Because the path from I to I is simple if there is not go through I in between. For each positive integer n, un is the sum of the weight of the simple path of the length n from I to n in automaton A capital. Indeed, since A is normalized to each simple path C from I to I in automaton A, our line corresponds a unique path from I to T in automaton A and conversely. Next, for any positive value R, let U and R be the sum of the weight of the path from I to I that go exactly R minus 1 times through I in between. We set UR of Z is equal such sum, and U 0 of Z is equal 1. The series U 0 of Z is equal to the following sum is the behavior of the automaton A, our line. Next, U R of Z is equal U of Z in R for any R equal or greater 0. Since the series we have for the series U star of Z is equal such sum, we obtain the U0 of Z is equal U0 such of Z, and this completes the proof of our proposition. Observe that the proposition is related to proposition 1.10.5, which can be used to give an alternative proof. If an automaton A is a normalized automaton, then in the automaton A star state I is not longer accessible and state T is no longer co-accessible. Thus the trimmed automaton is identical with a capital overline. Example: let us reconsider such u of z such form z plus z square. The weighted automaton A with A given on the left on the figure. Recognize that u with I is equal 1 and t is equal 3, yeah? The weighted automaton A, our line is represented in the second figure and on the right, yeah? The following statements are related weighted automata with weight in the set of of the same ring and with the non-negative matrices. We extend the definition of density matrix to the weighted automata. For weighted automata A capital, it is Q times Q matrix M defined by the following way. The entries is such in the place PQ is the following sum, where EPQ AQ is the weight of the edge PAQ. Proposition. Let U Z be an rational series recognized by the three weighted automaton A capital and M be the adjacency matrix of the automaton A capital. Then the radius of convergence of series U of Z is the inverse of the maximal eigenvalue of the matrix M. The proof. Let lambda be a maximal eigenvalue of the matrix M, which exists and is possible by the Perron-Frobenius theorem. So the Perron-Frobenius theorem states that any non-negative matrix M has a real equivalue M such that the model of lambda is less or equal rho M for any equivalue lambda of the matrix M, and the correspondence to M non-negative equivector V. Let rho be a radius of the convergence of the series U of Z, and for it PQ, let rho PQ be a radius of convergence series of Z. Then one device lambda is equal to minima of rho p of q, because this sum converges to for z with z model is less 1 divide lambda. Next, since the automaton A capital is trim, the series U PQ of Z converges whenever U of Z converges. Thus, we have that the radius of convergence rho PQ is greater or equal to rho for all states PQ. On the other hand, rho is greater or equal minima of PQ because U is a non-negative linear combination of the series as PQ. This implies that rho is equal minima of PQ, which is concluded the proof. Good. Now, so in next example, the weighted automaton A of the figure, following figure, recognizes the following series: U of Z, 1 divided of Z, or equal Z, is this following series. The radius convergence of the series U of Z is equal the square of 2 divided 2. The adjacency matrix of the automaton A is the following. The equivalent of this matrix is null and plus and square of 2 and minus square of 2. And so we finish our lecture. I wish you good luck and good health. Goodbye.